Alright everyone, welcome to my video for the last lab of Physics 2212, Lab 5, and we're going to be talking about Faraday's Law. So I wanted to show you all a formula of Faraday's Law. Of course there are many ways to interpret or to write Faraday's Law, but the general description I wanted to get across here is that there is a direct correlation between EMF and a change in flux. Of course, EMF also representing voltage, or an electromotive force, and dB over dt, obviously change in flux over time. There's a direct correlation there. Of course, N also in this formula represents the number of coils, which isn't necessarily part of this equation or part of this lab, but nonetheless, that's what that means. I wanted to specifically point out this negative sign here, and I wanted to talk about Lenz's law real quick too, in the sense that when a change in flux is presented to a system, nature doesn't really like that, and nature wants to resist or change in the opposite direction of that. So I just wanted to talk about that real quick. But as far as the actual procedure of this lab, we're going to take a bar magnet and take the measurements of it, mass, size, etc., and do the same for an aluminum foil tube. And we want to make sure that that aluminum foil tube is at least 1 centimeter thick. Record a video dropping the magnet through the tube, ensuring both the magnet entering and leaving the tube are in frame. Of course, you could also record the time while you do this. I figured, and at least what I did, was when you record a video, you can just look at the time change from that video. And then you want to repeat this step 2 5 times to get an average time it took for the magnet to traverse the tube. So pretty obviously, well, I guess intuitively, if you think about it, the magnet's going to drop the fastest as it just inserts the tube and fall slower towards the end. And of course, this makes sense given when the flux increases, the change in flux will increase, the force repelling the magnet will increase as well. So to kind of visually describe this, I found this video where a slit out of the tube, and as you can see pretty clearly, it accelerates at the top and then slows down towards the bottom. I also bring up this, recall there's a slit in this tube, I'm going to talk about that later. But I just wanted y'all to visualize exactly what's going on here in this lab. Okay, as a quick checkpoint, let's think about our results and what they could look on a broader scale. So if we used a ferrous tube, it could have induced a magnetic field upon itself, and that would add another layer of complicity, another layer of formulas, and that's the last thing I'd say we want on our last lab. So to reduce this complicity, our aluminum tube was a fine setup for this lab. And as you can tell by the previous video, as I touched on already, the magnet would fall much faster outside of the tube because it's just experiencing gravity rather than the change in the magnetic field that it would experience within the tube. So this is the data. For my experiments, I found the average drop time to be 1.24 seconds. From my glow script model, that expected time was 1.1 seconds. I'll include the link to the glow script in the description if you really want to learn about it. But given time parameters, I'm not going to talk too much about it. But I do want to talk about this velocity versus time graph. And this pretty accurately describes what's going on in real life. As you can see, we have a quick acceleration going down. And then the forces balance out more or less. And there's a constant velocity going down the tube. And then right at the very bottom, boop, falls out. So as I discussed, the computational model is pretty accurate. Something to note, even if you drop the magnet on the north side facing down, south side facing down, it doesn't quite matter because either way, you're still going to have a change in the magnetic field. The magnet's still going to float down. Now, if the resistivity of the conductor was close to 0, and of course that's included in my glow script model for aluminum specifically, if the resistivity was drastically decreased, well, the current would be very, very high, and you got to think, V equals IR for this equation. Thus, if you had such a low resistivity, the magnet would take a very, very, very long time to fall down the tube. Now, I mentioned the video for a specific reason earlier, and that was for this part right here. If there was a slot in the tube, if there were holes in it, whatever, the magnet would still fall and it would still float down, but there would be fluctuations. And of course, that video earlier was pretty good to describe that aspect pretty well in the sense that it still did float down, but of course, it would not be the most accurate way to do so. Thank you guys so much for watching. I hope you enjoyed this last video of our last lab. Good luck on test 3 and the final.